Okay, consider this function, the blue function, the curved function, the parabola. F of x equals 96x minus 16 squared. Okay, and you got two lines here that we've talked about, a secant line, the red line, and a dotted green line, which is the tangent line. Tangent line just hits at one point. Secant line goes through two. Okay, so we've talked about the concept that the derivative, in this case at 1, but we're going to generalize it, the derivative of the function is the slope of the tangent line. Okay, so the slope of that green line is the derivative of the function at that x value. Let me introduce our notation, f prime of x. Okay, so the slope of the tangent line at x equals 1 is f prime of 1. Okay, that's new. Now, let's come up with a way to figure out what that is, right? Because the equation of the secant line is easy. We know how to do that from algebra, right? If I said, give me an equation for the equation of that secant line, you would say, well, oh, I know that. M slope secant line equals y2 minus y1 over x2 minus x1. But we don't like this xy notation. We like function notation. So we would say f of 3 minus f of 1. Those are the two y values, and then 3 minus 1. Okay, but if I want to generate, let's say I'm going to show you the application that I have, and I can just move those dots around. So if I want to have a better rule for this, or to figure this out for any x value, so I would probably do something like this. I would start with, if I wanted to fix one point, but not the other, so let's say a would be 1, and x is x. X can move anywhere. Okay, and then what's the distance from x to a? Well, if you want, x right now is 3, but I can move it down here to 4 or 5. Okay, so x is just x, and 1 is just 1, but we could also move that point and fix it somewhere, so we call that x. We call that a. Okay, so how do I get, so that's the slope of the red line, the slope of the secant line. This big idea in calculus is to figure out from this formula what the slope of the green line is, the slope of the tangent line. Okay, so if I were to do that, I might go here and just say, well, this is actually what's happening. We're moving this point so it hits there, and it's a limit. The limit we want to take is what? What's going to 0? The distance between the two x values, right? The distance between the two x values. This distance right here is going to 0, or x is going to a. That's my first definition of derivative. X, which is right now at 3, is going to 1. That's a limit as x goes to 1, or as x goes to a. Okay, so that's my first definition. We're not actually going to use that, but does that make sense? I'm going to show you a better one here in a second, but I just want to show you all the definitions. We have 3 definitions. Well, really 2 definitions. See, you have the denominator is really kind of going to 0, right? As x approaches a, x minus a goes to 0. Okay, so if we wanted to fix that, so that's one definition, the slope of the tangent line, which, by the way, is the slope of the tangent line is a is equal to the derivative at a. That's what a derivative of a is. It's the slope of a tangent line at a particular point, which is also the instantaneous rate of change. We can tie this to our basic physics example. Right now, if this function represents a acceleration due to gravity problem, then the ball goes up, reaches a peak, its vertex, and then it goes down, hits the ground. The average velocity would be calculated by the red line, right? The change in distance, it goes from 90 to 200 or 140 in 3 seconds. So we could calculate the average velocity there. But If I wanted the instantaneous velocity when x is 1, I would need the slope of the tangent line. It's the same thing. What's the exact change in feet per second right here at x equals 1? And we can get that by doing what we're doing. Finding the derivative of that function when x is 1. Okay? All right, same thing. So the slope of the tangent line is instantaneous velocity is the derivative. All the same thing. All right. So back to my definition. There's one definition for the derivative. But I want to do a little bit better than that. I want to write this as a function. Okay? So instead of having to do that every time with one particular value of a, which I'm not going to make you do, I can just find a function that depends on x, like my regular function, that will, any x value I plug in will spit out the derivative value. That is the derivative function. This is a big deal. Okay, so I'm going to do it the same way. So right here, I'm not going to use a though. A represents a particular value. I'm just going to do this in a generic form where x represents any value that's in the domain of the function. Okay, so what I want to do is call this first point x comma f of x. All right, why am I doing that? Because if I moved it, then x changes along the graph. X changes, f of x changes. So what do I do with this point then? Well, this would have to be input what? Well, x plus some value. Okay, so right now h is the distance from here to here, the way I have it set up. But just picture those dots moving, and then just the distance between the 2 points, the x value of the 2 points is the distance we call h. Okay? And then, of course, if this is x plus h, then if I plug it into my function, the output is f of x plus h. Okay, that's how I choose to write my 2 points for my secant line. So now the slope of the secant line is f of x plus h, y2 minus y1. And then the change in x values is x plus h minus x. All right, x plus h, this is my x value. Remember, they're varying. They can go anywhere. And of course, x plus h minus x is just h. Okay, so that's the slope of this red line. Now, what happens when I move the red line to become the green line? What's changing now? So the way we said it before is x approaches a, which is still true, right? But the way I have it now, what's happening? What's going to 0? The distance between the two x values, which we called h, right? So I have a new way to represent this. We called that h. So what I'm doing now is I want to take the limit as h goes to 0, which is the same as x goes to a, of my secant line. And what I have now is this, and I'm going to show you this is actually a function of x. And this is my derivative, not at a particular value a, but at any value x. Okay? That is not just the slope of the green line, but the slope of the green line in this picture, but the slope of the green line. Move this guy here. The slope of this green line, right? It'll depend on, in this case, x is 4, but my new definition will give me a derivative function for any of these values, and I can just plug it in. Okay, so what you're not seeing on the graph is the derivative function itself. We'll talk about that later. We're just seeing the result of plugging something into the derivative function. Right now, I would be able to get the slope of the green line using that formula. Okay, and that's what we're going to do next. Let's see if we can actually do one. So, can I find that derivative function? So if I wanted to find that for this particular problem, well, let's just make it a little bit easier. Let's say, let me make those numbers a little smaller. Let's say I give you this function. Let's say 4x minus x squared. All right, and I want the derivative. So what would I do? I would try and figure out this formula, and this is why we did this difference quotient thing before. Now we can use it. I wanted to do, let's do 4 minus x squared. 4 minus x squared. Let's find the derivative function. So what I do is just find f of x plus h. This is called the difference quotient. You've probably seen it before. Okay, so let's do my first example here. It's 4 minus x plus h squared, which is 4 minus, FOIL this out, x squared plus, remember x plus h squared is x plus h times x plus h, which is x squared plus xh, that's 2 of those, plus h squared. Okay? And then if you want, you can run the negative through. We'll have to do it at some point. So now I can find my derivative function. The first derivative in the class is going to be 4 minus x squared minus 2xh minus h squared minus f of x, which is 4 minus x squared, all over h. And I got a mistake here. What is it? That's not the derivative. That's just algebra. The derivative, I forgot, and don't do this, is the limit. This is important. The limit as h goes to 0. Okay, let's see if we can figure that limit out. So I have, if you run this through, you get negative 4 plus x squared. So 4 minus 4 is 0. Negative x squared plus x squared is 0. It just leaves me with the limit. Don't forget to write that. That's important. I forgot last time. The limit as h goes to 0. We haven't taken the limit yet. We haven't done calculus yet. We're just doing algebra. That's it, right? Over h, which is equal to the limit as h goes to 0 of, and then I can divide h into here, and one of those goes away, and it's negative 2x minus h. And now I can take the limit as h goes to 0. Good news, one of our limit methods we learned previously was just to plug it in, as long as it doesn't give us any issues. And that's what I'm going to do here. H goes to 0, that goes away, and I get my derivative function, negative 2x. Okay, which is the slope of the tangent line or the instantaneous rate of change for any x value. This gives me the slope of the tangent line for any x value. That's why it's so powerful to find the derivative as a function of x, because now I can pick my a values and figure out the derivative for any point, right? F prime of 1. Negative 2 times 1. F prime of 2, negative 2 times 2. F prime of 0, negative 2 times 0 is 0. Okay, so in the next video we'll do more of these. You're going to have to do a bunch of these. This is called the derivative by definition, using the definition of derivative. And then later in the class, we're going to learn like shortcuts. So you won't have to do this all the time. We got some real nice shortcut formulas. But what I want to do in the next video is just do some more of these and then look at the graph. We really want to look at the graph and see what's happening at x equals 1. Can I see that slope of 2 there? Okay.